In this video, I show you how to integrate via trigonometric substitutions. This is particularly useful for certain type of integrals where the integrand contains a difference or sum of squares. Now, trigonometric substitution, we pretty much use this technique whenever we replace the variable of integration, which I'll call x, by a trigonometric function of an angle, let's say theta. Now, the typical substitutions are x is a times sine of the angle, tangent of the angle, or secant of the angle, and they are particularly used in the cases where you see one of these three forms present in the integrand. So you see a sum or difference of squares of x squared and a squared. In particular, and to make the correspondence between the substitution and when it's used very obvious, consider when x is a times the sine of theta. In that case, a squared minus x squared is the same as a squared minus a squared times sine squared. But if you factor out the common factor of a squared, that's the same as a squared times the quantity 1 minus sine squared, but 1 minus sine squared is cosine squared. So you get that a squared minus x squared is the same as a squared times cosine squared. Notice by using the substitution that we remove the difference between two objects and turned it into a product. You'll see then that if you use the other substitutions in the case of x equals a times tangent of theta, that a squared plus x squared becomes a squared secant squared, and in the case of x equals a times secant of theta, then we have that x squared minus a squared simplifies to be a squared times tangent squared. In all cases, the difference or sum of squares is converted into a constant multiple of some trig function squared. But in any substitution in our integration, we want it to be reversible so that we can return back to the original variable x. For this reason, the trig functions we use must be invertible functions. So, in particular, if x is a times the sine of theta, that requires that theta is going to be the inverse sine of x over a. But then the angle theta must be greater than or equal to negative pi over 2, but then less than or equal to pi over 2, or else we can't use the inverse sign at all. Using the same exact reasoning for the others, x would then be equal to the a times tangent of theta would then require that theta is equal to the inverse tangent of x over a, and theta would then be greater than negative pi over 2, but less than pi over 2, or else we could not use the inverse tangent at all. For the same reason, x is equal to a times secant of theta would then require that theta equals the inverse secant of x over a, but this time the angle range for inverse secant is 0 to pi, including 0 and pi, but not including pi over 2, and the result depends upon the sign of what the inverse secant is applied to. So if x over a is greater than or equal to 1, then theta would be greater than or equal to 0 or less than pi. But in the other case, if x over a is less than or equal to negative 1, then theta would be greater than pi over 2, but less than or equal to pi. For this reason, whenever we use a secant substitution, we have to be really careful with the type of values we're using. Almost always, in fact, you'll notice that your book will automatically limit the problem so that you only have to worry about the first quadrant case, that is where x over a is greater than or equal to 1. So the angle range is only in the first quadrant, from 0 to pi over 2, including 0, not including pi over 2. In the case of indefinite integration and or antiderivatives, in order to return to the variable x, you're going to use identities to rewrite your answer in terms of the angle theta first. Then once you have that result, you can then use these reference triangles to help evaluate the trigonometric functions you see in your answer. In the case of using x equals a times tangent, if you draw this picture, notice the highlighted red legs. So from theta's perspective, the opposite side is x, the adjacent side is a, so the tangent of theta is x over a. You can get the remaining blue side by just using the Pythagorean theorem. In this triangle, notice the red sides. From angle theta's perspective, x is the opposite and a is the hypotenuse. Well, that means then x over a is the sine of theta, and you get, of course, x equals a times sine of theta as our substitution. And you can get the remaining blue leg, once again, by using the Pythagorean theorem. Lastly, if we use x equals a times secant of theta, notice if you draw this triangle with the red highlighted sides, a then will correspond to the adjacent side. X would be the hypotenuse, so x over a, hypotenuse over adjacent side, that's the secant of theta. So then you can get the remaining leg, just once again using the Pythagorean theorem. Notice in all these cases I've also included the most common place that you would use these particular substitutions, because you see them a lot when you see a square root of a sum or difference of squares. In each case, notice that I have to put an absolute value around the trig function because normally the angle range might be quadrant 1 or another quadrant. So when you take the square root of the secant squared or the cosine squared or the tangent squared in the simplification of the square root of that sum or difference of squares, the square root and the square don't cancel. They leave behind an absolute value. So many times in the integration, we have to come back and argue whether we can get rid of the absolute value or whether we need to put an extra minus sign somewhere. I've now reviewed enough so that we can now begin the process. The general procedure then to do an integration for an indefinite integration is to first write down your substitution, determine your dx, and then remember to specify the values of theta that's being used in that substitution. We'll often need to recall that later on in the process. Then just substitute everything in, whatever you have for x, whatever you have for dx, and simplify the entire expression. Again, as you do so, remember the angle range. Integrate the new trigonometric function. Please keep in mind as you do so, once again, the restrictions on the angle. And finally, draw an appropriate reference triangle to reverse that substitution. In order to do that, you first have to take your answer, which right now should be a function of theta, and make sure that all the trig functions are sine of theta, tangent of theta, secant of theta, things like that. You can't have sine of 2 theta. Just use some identity to remove it, and then once you've done so, you can then write down your final answer in terms of x. This is how it's done in general for indefinite integration. Definite integrals have a slight little twist to it. Let's then pursue how to go about finding the value of this indefinite integral. Well, I would try my normal process first, but none of the normal steps would actually simplify and go anywhere. There's nothing to do here in terms of simplification or expressing it as a product or looking for a u substitution. Certainly parts might be something I want to try, but I see a x squared over a square root. I don't feel like integrating any part of that, although you actually could if you wanted to. Instead, I'll jump right into then just using trigonometric substitution. So I noticed then that this part is of the form a squared minus u squared. That's where a equals 4. So I'll try the corresponding substitution of that form. For a squared minus u squared, I use x is equal to a, which here is 4, times the sine of theta. And remember, I have to make sure that the theta here I can solve for it. So I have to have the angle range be restricted to the inverse sine. So that's from negative pi over 2 to pi over 2 inclusive. Also along the way, I'm going to need at some point what is 16 minus x squared. So I might as well just figure that out now. You might notice though that the result would be 16 times cosine squared of theta. So this will then become, since dx is equal to 4 times the cosine of theta d theta, the integration now becomes, using all this as preamble, the integration of the x is squared, so that's 4 squared times the sine squared of theta. I have a square root of the 16 cosine squared of theta, and then the dx is a 4 times a cosine of theta d theta. That would then simplify to be the antiderivative of, I'd have a 16 sine squared of theta all over a 4 absolute value of a cosine of theta. Don't forget, the square root of a square does not cancel, it gives you an absolute value. And then you have 4 times cosine of theta d theta. But because of the angle range I'm using, That's from negative pi over 2 to pi over 2. Cosine is already positive, which means that this is actually already positive. So I don't need the absolute value. That means then the cosines will cancel, giving me 16 sine squared of theta d theta. And that's using trig substitution. All I did was use some kind of trig substitution in order to remove the difference of squares. Now I go back to what I learned in the previous section, how to integrate products of trig functions. So for trigonometric integrals, the first technique is the save it technique. Well, that only works if it's a product, and for sines and cosines, I need one of the powers to be positive and odd. That's not true. So I go on to the next case. In this case, I'm looking for products of sines and cosines where both powers of sine or cosine are non-negative and even, and that's what happens here. So I'll try the power reduction identities. This is then the integration of, you would get 16 times 1/2 times 1 minus the cosine of twice that angle, d theta. So continuing that over here, because I'm going to need the room, that would then equal the integration of 8 minus 8 times the cosine of 2 theta d theta. That's just distributing the product. Integrating each of those pieces gives me 8 theta, and then I have minus of 4 times the sine of 2 theta plus c. And that's the antiderivative of that expression. That's the answer, at least in terms of theta. We now have to go back and find out what it is in terms of x. Well, to do that, I can't leave sine of 2 theta. So I will write this one more time as 8 times theta. Remember, the sine of 2 theta, that would be 4 times 2 times the sine of theta, the cosine of theta, using the double angle identity. So that then equals, I have 8 theta minus 8 times the sine of theta, the cosine of theta, plus c. Okay. You now have a choice. If you go back and draw a reference triangle, that's where this is theta, and this is a right angle. We just have to make sure that the sine of theta is x over 4 because of what you see right here. So the sine of theta just has to be x over 4. So sine of the angle is the opposite over the hypotenuse. So this would have to be x, this would be 4. And using the Pythagorean identity, this will then give you the square root of 16 minus x squared. From that, I can easily determine what is sine and what is cosine. So our answer then is going to be equal to 8. Theta equals the inverse sine of x over 4. We get that from this. So that's the inverse sine of x over 4. To that, we subtract 8 times the sine of theta, which we know is x over 4, and the cosine of theta, which we can get from the triangle to be the opposite side, x over the adjacent side. Oh wait, it's the adjacent side, which is the square root of 16 minus x squared, all over the hypotenuse, which is 4. And then we add on c. So our final answer should be 8 times the inverse sine of x over 4 minus, I'd have x times the square root of 16 minus x squared. In the denominator, I have 4 times 4. In the numerator, I have an 8. So I'm dividing by 2 and adding c. That's the answer to the problem. Notice it's quite involved, isn't it? There's quite a bit of trig involved in this process. And you need to know how to integrate trigonometric integrals, because trigonometric substitution just converts the old integral into a trigonometric integral. So let's do this particular indefinite integral. Once again, I would go through our normal process, but eventually when I'm going through the substitution phase and looking for integration by parts and looking for maybe clever multiplications, I would notice that I have a difference of squares inside a square root. That cries out to use trigonometric substitution. So I notice that the expression you see here has the form y squared minus a squared, and that's where a is 5. So that leads right away to try the substitution. Y is equal to a, which is 5, times the secant of theta. But if you solve for theta here really quickly, notice that theta would then equal to the inverse secant of y over 5. But since y is greater than or equal to 5, then the y is actually over 5 is greater than or equal to 1. If you take the inverse secant of a positive value, the angle's in the first quadrant. So this is the case where theta is greater than or equal to 0, but less than pi over 2. Just remember the angle range, we might need it later on. Okay, well, I also need to know what is dy going to be, and that's 5 times the secant of theta, the tangent of theta d theta. And also, I need to know what is y squared minus 25. I'll just do that simplification right here. And from the previous work I've showed you, that has to be 5 squared, which is 25, times the tangent of theta squared. Okay, so just plugging everything in. Using all this as a preamble to what I've about to do, I will rewrite the integral once as I need to do so, as there's no way to connect the two statements now. So I'll write the integration of the square root of y squared minus 25 all over y squared dy is the same as the integration of the square root of 25 times the tangent squared of theta all over y squared. So y is 5 times secant of theta. So squaring that gives me 25 secant squared of theta. And dy is 5 times secant of theta tangent of theta d theta. Now that would then equal, in the numerator I'd get the antiderivative, in the numerator I'd get 5 times, now that should be the absolute value of tangent, because the square root of a square doesn't cancel. You get the absolute value of the expression. So it should be the absolute value of tangent. But because of the angle range, that's the first quadrant. In the first quadrant, tangent is positive anyway. So I do not need the absolute value around the tangent of theta. The 5 and the 25 cancel, give me a 5. A secant divided by secant squared gives me a secant in the denominator, and it's still multiplied by yet another tangent of theta. That would then equal the integration of, I'd get tangent squared of theta all over secant of theta d theta. And that's basically the idea behind trigonometric substitution. You're just converting the old integral into a new trigonometric integral, and we used the techniques you learned last section to find this one. Well, actually, you didn't need to actually use the techniques I taught you last class to find this particular integration. Notice that I can, if I wanted to, convert this entire integrand into one trig function by using a Pythagorean identity. And then, by doing so, I can then separate the fraction, giving me an integration or a sum or a difference. That sounds like a good idea, so I'll pursue that. This would then be equal to the integration of, it's the secant squared of theta minus 1 all over secant of theta d theta. I can then divide the secant into each term to get the secant of theta minus, well, it would be 1 over secant. Oh, not minus. Well, I put a plus. It would be minus. It should be 1 over secant. But 1 over secant is just cosine. So I'll skip that little simplification step, d theta. And now we can easily integrate each of those pieces. That will then just be equal to, the antiderivative of secant is natural log absolute value of secant of theta plus tangent of theta. Then you have minus, the antiderivative of cosine is sine of theta plus c. That's the answer. Well, I mean, that's the answer in terms of theta. I have to go back in terms of y. So to do that, remember that 5 times secant is y. So in particular, the secant of theta is just y over 5. I'll build a little right triangle where that is true. Here's theta. Here's my right angle. So the secant is the hypotenuse over the adjacent. So this is y. This will then be 5. And the remaining leg can be found by using the Pythagorean theorem. And that has to be the square root of y squared minus 25. Remember now, this is just a representation of the actual different values. So keep that in mind as we do the problem. So this then equals, I have the natural log of the absolute value of the secant, but secant is y over 5. I already know that. And tangent of theta, by looking at my triangle, that's the square root of y minus 25 all over 5. And then I have minus the sine, and the sine is the square root of y squared minus 25 all over the hypotenuse, which here is y. And then I add c. That's it. That's the answer. That is the particular antiderivative of the original function. Let's do this indefinite integral. Now, there's at least two ways to approach the problem. Notice that here we don't have a single variable being squared plus a constant squared. Certainly there's a constant squared, it's just 1 squared. But we don't have a single variable squared. So there's two ways to look at the problem. One way is to rewrite it first. So I'd rewrite this as 1 over, you could take the 9 out of the square and get 81 times t squared plus 1/9, that quantity squared, dt. By doing so, you notice that this has the form of t squared plus an a squared. That's just where a happens to be 1/3. So I can use this substitution, t equals a times tangent of theta. So that'd be t equals a 1/3 times the tangent of theta. Or in other words, 3t equals the tangent of theta. That's one way to look at it. Another way to look at it is to notice that the integration in the integrand, you could instead think of the expression being squared, this part right here, as a u squared plus an a squared. That's just where u would be 3t and a would be 1. So, in that kind of substitution, if u squared plus a squared is our particular pattern we're looking at, the substitution should be u equals a times tangent. So I would have u, which is 3t, is equal to a, which is 1, times tangent. Notice, either way, we get the same result. Because of that, almost always, I look at the process like this. So, now you see what I intend to do. Let's go ahead and tackle the problem. So, the integration of 1 over 9t squared plus 1, that quantity squared dt, we'll be using that 3t is equal to the tangent of theta, or in other words, t is equal to 1/3 the tangent of theta. That means that the angle range here is understood to be from negative pi over 2 up to pi over 2, and dt would equal 1/3 secant squared of theta d theta. All right. We also, though, need 9t squared plus 1. That's the same as 3t squared plus 1. That's tangent squared plus 1. That's just secant squared of theta. So using this as preamble for our trig substitution, this would then become equals, that'd be the integration of 1 over a secant squared of theta, that quantity squared, times dt, which is 1/3. Notice how I wrote the fractions so the fraction bars line up. Times the secant squared of theta d theta. And that then equals, that'd be the integration of 1/3, and you'd have 1 over the secant squared of theta d theta. So we have to figure out how to do that integral. Notice I did not put the 3 here in the denominator because I'm choosing to leave the constant out front because I'm going to do that in a minute anyway. This could then be, notice 1 over secant, we know is cosine, so that's 1/3 the cosine squared of theta d theta. And we know how to integrate that. We replace the cosine squared with a 1/2, 1 plus the cosine of 2 theta d theta. And that would be the integration of 1/6 plus 1/6 cosine of 2 theta d theta. So continuing from here, that would then be a 1/6 plus a 1/12 sine of 2 theta plus c. That's the antiderivative. So that's the answer. Well, that's the answer in terms of theta. We have to go back to t in this case. To do that, though, I have to get all the trig functions being applied to only theta. In this case, I have to get rid of that sine of 2 theta. I recall, then, that the sine of 2 theta is 2 times the sine of theta times the cosine of theta, and then we have our plus c. So that is 1/6 plus 1/6 the sine of theta, the cosine of theta plus c. Okay. Okay, well now if you go back to the beginning here, you see that the tangent of theta is 3t. That's really the tangent of theta equals 3t over 1. So if we make a little triangle where this is theta, this is a right triangle, the tangent of theta is 3 over 1, so that's 3t, the opposite 1, the adjacent, and the remaining side would then be the square root of 9t squared plus 1. So this would then be our answer, is 1/6 plus 1/6. The sine of theta is the opposite in that triangle, 3t, over the hypotenuse, square root of 9t squared plus 1. The cosine would be 1 over the square root of 9t squared plus 1. And then, of course, we have plus c still. So our final answer after all this work is 1/6 plus 1/6 times a 3t over a 9t squared plus 1. And, of course, you can simplify the 3 and the 6 if you want to and cancel them out to make that become a 1/2 instead. And you have plus c here at the end. I just ran out of screen. And that's the answer to that problem. Okay, so we worked up to doing a particular definite integral. Let's find this one. Well, you should notice right away that I can make a substitution. U is equal to the natural log of x, so that du will equal to 1 over x dx. And since I'm changing the variables, I might as well just change the bounds. So x currently goes from e to e squared, and that means u will, of course, go from 1 to 2. So the integral now becomes the definite integral from 1 to 2 of a square root of 4 minus u squared all over u du. Now in this particular problem, notice that since I changed the bounds, I never have to go back to x ever. In fact, it's better just not to. For this new integral, I see that it looks like I'm going to use a trig substitution, and that's because this has the form, I have an a squared minus a u squared. That's where I have a squared for a squared minus a u squared, and that's just where the a would be 2. So I'll try u is equal to 2 times the sine of theta. Now that also means then that the square root of 4 minus u squared would have to be 2 times the cosine of theta. There should be an absolute value around that cosine, but the angle range is going to be between negative pi over 2 to pi over 2, because I need to be able to solve for theta. In order to do that, I need to be able to use the inverse sine. That's the angle range we use for that. Now also, and because of that reason, since the angle is in this range, that means the cosine is already positive, and I don't need the absolute value around this cosine. At the same time, though, we would have that du would equal to 2 times the cosine of theta d theta. And when we change the variables, we can also change the bounds. So we have theta values and u values. And noticing that u is equal to 2 times the sine of theta, that then means that theta would just be the inverse sine of u over 2. And since u is either 1 or 2, just by plugging it into this formula, you get theta equals the inverse sine of 1, which is pi over 2. Or you have that theta equals the inverse sine of a half, which is pi over 6. So then this is the same as writing the integration of pi over 6 to pi over 2 of, well, the numerator would be 2 times the cosine of theta that u is 2 times the sine of theta, and the du is 2 times the cosine of theta d theta. So just cleaning that up, that gives us the integration from pi over 6 to pi over 2 of 2 times the cosine squared of theta all over the sine of theta d theta. I'll just put little boxes around the work. This was for the first integral. All this mess here, this was all for the second integral. Now, you might wonder, do I have to do this? Do I have to change the bounds? Well, if you start with a definite integral and you change the variables, then yeah, you got to change the bounds. But you don't have to do this. What you could do instead is do all the exact same work, just don't change the bounds, and instead just start from the integral of 4 minus the natural log squared of x all over x times the natural log of x dx. And then after a lot of work, you would basically get the exact same integral. You'd get the integral of the cosine squared of theta all over the sine of theta d theta with a 2. You could then find that particular antiderivative. But the disadvantage of using this technique is that eventually I'm going to have to go back to x. Because I have to go back to the original definite integral, find the expression in x, and then evaluate it at e and e squared. So that sounds like a truly terrible thing to go through. So I'm just not going to do that. You can, though. You can take this alternate track if you wish. But really, when you use substitution, if you can, as you change the variable, change the bounds. Now, the only time I don't do that, when I change the variable, change the bounds, and just do the antiderivative by itself, and then come back and evaluate at the bounds, is when I change the bounds, that the values you get here or here are just awful. If they're really long, nasty expressions, you'll have to write it every single time you do a new step in the integration, and that sounds like a terrible thing to go through. You'll notice that a lot of your problems in homework are not like that. A lot of them, when you change the bounds are very timid numbers, like you see right here. So in that case, I almost always do them for the problems that you have in this course. In real life, though, it might be better to just do the integration and then just use the original bounds in your evaluation. So continuing here, this is then going to be the integration of pi over 6 to pi over 2 of 2 times. Now, that is a product, or at least you could think of it as a product, of sines and cosines. But if you do so, notice that the power on sine and cosine, neither of those powers, is positive and odd. The power on sine would be a -1, because you have to bring the sign up to turn it into a product. And the power on cosine is unfortunately positive, but even. Also, since the powers on sine and cosine are not both non-negative and even, I can't use the power reduction technique. So the save it technique won't work, and also the power reduction technique won't work. So I'm kind of left with trying to convert this particular expression into something that's equivalent to it using the identities. I noticed right away, though, that you can write cosine squared as 1 minus sine squared of theta over the sine of theta. This sounds like a good idea, because then I can separate the fraction and convert this into 2 integrations. So this is the definite integral from pi over 6 to pi over 2 of 2 times. I would get, well, sine of theta divides into 1. That gives me cosecant of theta. And then you would have a minus a sine of theta squared divided by sine of theta. That's the sine of theta d theta. And that would then be 2 times. Well, to find the antiderivative of the cosecant, there's actually lots of different versions of it. I'll just give you one of them. It winds up being that it just is a good choice for this problem. One such answer would be negative the natural log absolute value of the cosecant of theta plus the cotangent of theta. And then I have the antiderivative of sine is negative cosine, but I already have a minus, that's a plus cosine of theta. And I have to evaluate that from pi over 2 pi over 6 to pi over 2. Alright, so then that would then be equal to, if I just plug in, if I evaluate at pi over 2, I would get negative natural log absolute value of cosecant of pi over 2 is 1, cotangent of pi over 2 is 0, plus cosine of pi over 2 is 0. And then I have minus 2 times negative the natural log absolute value of. I then have the cosecant of pi over 6, which is 2, plus the cotangent of pi over 6, which is square root of 3. And then I have plus the cotangent, the cosine of pi over 6, which is square root of 3 over 2. And that's the answer. We just have to go back and simplify this horrible mess. So that's the same as writing, well, the first part's all 0. That's a 0. Natural log of 1, that's 0. 2 times this is 0. So we ignore all that. It's double negation makes it positive. So it's 2 times the natural log of, oh, I should get rid of that parenthesis. 2 times the natural log of the absolute value of 2 plus the square root of 3. And then I add, not add, because I have to distribute that minus 2 through. So I have negative 2 times that plus square root of 3 over 2. The 2's cancel, leaving me negative square root of 3. And that's the answer, or at least that's one version of it. And that gives you a basic overview on how to do integration via a trigonometric substitution. Notice the overall goal is just to go and turn the original integral that had a sum or difference of squares into a trigonometric integral, and then we use previous techniques to integrate that. Please also notice that there's bounds. The better way to handle these problems, as long as the bounds don't get too terrible, is to, as you change the variable, just change the bounds so that you don't have to go back to the original integral.